thanks to the light-matter interaction that we were able to understand how the atom is built up and how electrons and protons are communicating or interacting with each other. So in order to understand this phenomena, we have two things. We have light interacting with atoms. So we need to understand the nature of light and then use this understanding to understand the composition or the structure of the atom. The nature of light was always thought by physicists to be simply waves. So any light is a wave, and waves are mathematically described with an equation that is called a wave function. So we want to develop an equation that describes the motion of that wave. Any wave function describing a wave is simply a relationship between the displacement, which is the magnitude of the y-axis, versus time, which is the magnitude of the x-axis. So when you plot a relationship between the displacement and time, you see that the wave will follow a sine function, as you can see right here, which mathematically can be described as displacement y equals a constant, sine 2 pi mu t. So the only parameter that determines the displacement of the wave in this case is going to be actually the frequency of the wave, which we give the symbol of nu. So nu is the frequency of the wave, or how many pulses of that wave occur per second. And it has the unit of second minus 1 or hertz. So in order to describe any wave, you only need to describe or determine its frequency. From the laws of waves, frequency equals the speed of the wave divided by wavelengths. So you can express the displacement of the wave as a function of wavelengths, just in the same way we described it as a function of frequency previously. So wavelengths in this case is going to be simply the length of a complete wave, or the distance between two identical points on the function that describes a wave. And wavelengths is a length, so it will have the unit of a length, which is meter, but typically in the atomic theory discussions, we deal with much smaller wavelengths, so we usually express them in fractions of a meter down to nanometer. And the third parameter that can equally describe any wave is the wave number, which is simply the inverse of the wavelengths, the number of waves that occur per meter for that wave. And the unit of wave number, since it's the inverse of wavelengths, is inverse meter or inverse centimeter, or sometimes we simply call inverse centimeter wave number. So you can define your wave equally by any one of these three parameters because they are mathematically related to each other. You can define it with frequency, nu, which we defined previously as the number of pulses per second, or you can define it by wavelengths, which is the length of one pulse of that wave, or we can define it by wave number, which is the number of waves per 1 meter. So the first skill that we need to learn about waves is how to interconvert between these three parameters: frequencies, wavelengths, and wave numbers. And the relationships are straightforward. So let's do an example on these types of calculations. If you know that a photon of light has a wavelength of 325 nanometer, what would be the frequency? And we know that the speed of light is 2.99 times 10 to the power 8 meter per second. And nanometer is 10 to negative 9 of a meter. First step is going to be converting nanometers to meters using the SI prefix conversion factor. So you multiply it times 10 to negative 9 meter divided by 1 nanometer. Nanometer will cancel out with nanometer, and now you have your wavelengths in terms of meters. And we know that frequency equals the speed of light divided by wavelengths. So we'll take the speed of light, 2.99 times 10 to the power 8 meters per second, and then divided by the value of the wavelengths, which is going to be 3.25 times 10 to negative 7 of the meter. So you can see that meters will cancel out with meters, and you will be left with a number in the unit of second minus 1, or sometimes we call it hertz.